This video will show you how to use the Clemson Slug Test datasheet. The datasheet is designed to be used in the field for recording data, recording the information that you need to know to analyze the slug test, and then doing the necessary calculations to come up with the results. So the very top of the sheet has information about the well, the location, who conducts the test, and when. This just really is background information about the test. And then you want to fill in the initial depth to water. That goes here, and that'll be some important information for the calculations. The volume of the slug and predicted initial displacement, if you want to include that, would go here. The casing elevation is here, and for our applications we won't be using that information. The length of the screen, water table at the bottom of the screen, this will be important information. And the length of the screen is shown here in this sketch right there. That's going to be LE, L sub E in the subsequent calculations. The water table to the bottom of the screen is written here, and you can see what it is, 80 feet in the application or the example that we're going to do here. And then the saturated thickness is B. Diameter of the casing is put there. That will be capital, or that'll be lowercase d sub c, and the diameter of the well itself is uppercase D. The results will be summarized here, and then the data that is recorded in the field and then analyzed is here on these columns. What I recommend doing is recording the data as it's read off in the field, and the elapsed time since the slug is put in is in this column, and the depth to water is written here as it occurs in the field. And then during the slug out, I usually leave a gap, and then as the slug out occurs, this is the time since the slug was first put in, so the elapsed time. So if you're using a watch, this is easy to record with a watch. And then this is the depth to water. And to work the data up, you determine the time since the the time since the slug was first measured, the time since the first measurement was made, so that this becomes 0. And basically then this time is subtracted from all of these, and that result is written here. And you do the same thing for the slug out, but you start with the first reading of the slug out period. So this starts at 0 and increases. Then the hydraulic head is determined by taking the depth to water at the first measurement. This is after the slug has been put in, and using the depth to water initially, and so that's written right there. And so that value minus that value gives the hydraulic head, and that's written there. So work the data up, and then do the same thing for the slug out, and it's negative because the head's dropped when you pull the slug out. And then this is the hydraulic head at the in this column, normalized by the first hydraulic head. So it starts out at 1, and then this value here of 0.86, for example, is 3.46 divided by that value. And similarly down here, you've normalized the data using the first value during the slug out period. So that value there, 0.74, is this value minus 3.13 divided by minus 4.22, and the minus signs cancel out and you have positive values here. So there's the data worked up, and then to analyze it, you'll plot h over h0 as a function of time for the slug out, and for the slug in, you'll have this value, these values of h over h0, and these values of time. Those are plotted on the graph on the following page. The first point should plot right here at x equals 0, y equals 1, and then the rest of the points plot down like this. And in this case, they form a nice straight line, but often in field data, they don't. They form somewhat of a curved function, and so you would do a best fit line through them. And I would typically weight the points up here for most of the applications. What we see in the wells around here is they often have a long tail, and so the points, rather than drop off like this, they drop off more like that. And so fit the data with a line using these points up here, particularly if they're forming a nice straight line. And then to analyze the results, you need t.37 first. So this is 0.1. It's a log scale, so 0.2, 0.3, and 0.4. This dashed line is t.37. So go across and down, and that's t.37. This is h over h0 equals 0.37. So the head has dropped to 37% of the initial head right here, and that occurs at this time. Put that time there because we'll use it later. And then the Hvorslev analysis, and really all three analysis, will use this basic equation right here. This is the diameter of the casing squared, and that's t.37, and this is the geometric factor. So determine the geometric factor for the Hvorslev equation using this equation here, and these terms are defined on the previous page. That's the length of the screen, and this is the diameter of the well itself. So capital D is that diameter. And you get your result, put it here. The Defax method uses this same formula. It's been cut off, but that's shown right here on the worksheet. You should be able to see it clearly. And in this case, what we did was determine R sub E, the geometric factor, using a numerical model, and we found that it ranged over this range for many typical cases. And so what I would recommend is just using a value of 1.0 for RE as the default. That gives you this value of for the transmissivity. So the Bouwer and Rice analysis, this is the more complicated analysis, but it also gives you the most detail in terms of geometry. It'll use a well that has a screen that's, the top of the screen is below the water table, and the bottom of the well is below the bottom of the aquifer. So ultimately, you're going to solve this equation, which is the same equation that we had before, with one important difference. This T sub C is the time that it takes for the H over H0 to drop one full log cycle. So extrapolate this out and determine the time to go from here to here. In this case, it's 46 minutes. So 46 minutes goes right there to keep track of it. And then you need to go and do these calculations in order to work your way down to this final calculation. But that'll be 46 minutes. Oops, and I see a problem here. Just a second. And so the Bouwer and Rice analysis requires that we calculate the time, the characteristic time, a bit differently than Hvorslev. And it also requires that we calculate a geometric factor using a little bit more involved procedures than in Hvorslev or the other method, the Defax method. And I think it's understandable that the method would be a little bit more involved because the geometry is a bit more complicated here for Bouwer and Rice. So what you need to do is determine the characteristics of the geometry. So in step number 3, if LW is less than B, then you have to determine the constants A and B and do this calculation. So let's see, if LW, this is LW, and if that's less than B, then you do this example. The other case is if LW equals B, so this and this are equal. And in that case, you do you determine C here, and you do this calculation. So in our case, for the problems down at the Clemson Bottoms well field, this will be true. LW will be less than B, and we'll do this analysis. So in order to calculate this, we have to first come down here and determine these constants A and B. So here's the way you do it. You have to determine this term, 2 times LE divided by D, and for the dimensions of this problem, that's equal to 240. So we come here to this graph, and this graph was determined by Bouwer and Rice. And so you come across here to 2LE over D equal to 240, and that's the red line. The red line intersects this line here that's B values, and this line that's A values. So B values are read off where you go to this intersection and go off to the right here. There it says B. And you go to this intersection and go to the right or to the left, and there that says that's A, the values of A. And when I did this, I got values of 6.2 and 1.1. I can see actually this looks like B is equal to 1.1, but I think what happened was this green line should be up a little bit higher. It looks like it should be up a little bit more and equal to 6.1. It looks like more like 5.7, but I think that's just a graphical slip. I had some difficulties when I was drawing these lines out in PowerPoint. So read the values off of these graphs and write them here, just so you have a record of what those values are. These are the values that I used up in this calculation. So the next step then, once we determine A and B, is to calculate this term beta. So this is the formula, and it looks somewhat involved, but it's pretty straightforward. You just need to plug in these values here, and this is the formula for beta, where there are blanks in values that you need to plug in, and these are all from the geometry of the problem. So LW is 80 and capital D is 0.5 and so on. A and B go in here, and then you go through and do the calculation. Don't forget that all of this stuff, it's 1 over all of this stuff. Okay, so don't forget that last operation. This is in the denominator. So the result here is 4.22, and that's the geometric factor beta. That goes down here, and RE, this geometry term, is calculated using this formula. So there's 422, and here are these other parameters. It comes out to be 1.6, and that gets substituted in here. These are the values of the diameter of the casing here, and then 46 minutes as the characteristic time from here that we determined from the previous page. So if you go through and do those calculations, you get this result, 3.44 times 10 to the minus 3 feet squared per minute. Then what I would recommend doing is take this value and take that value and this value and this value and write them out here, so you've got them all summarized on this page. Now what you can do, remember we've got 2 tests here, one for slug in and one for slug out. If the values plot, if the curves plot pretty close to one another, then you might just take the line that fits both of them. But if they're a bit different, then you might take a line that fits each one and go and do the calculations for both slug in and slug out. Sometimes that you do get differences between the two slug in and slug out. But for the most part, they're pretty close. Okay, so what you'll end up with is at least 3 different estimates of the transmissivity, possibly 6, from this single test, all depending on whether you're using slug in and slug out or which one of the 3 methods that you use for analyzing T. So what I would recommend doing at this point is using for calculations, you have a problem now. Which one of these do you use? They'll be somewhat different. And so one of the things that you can do is combine them into an average value of hydraulic conductivity. And the way this is typically done is to use the geometric mean. We saw earlier in the class that if the system is layered, that we might average the hydraulic conductivity using one method parallel to the layers and one method perpendicular to the layers. But in this case, we're not really sure about that, and so an alternative approach that's often used for averaging hydraulic conductivity, different values of hydraulic conductivity, is the geometric mean. And so the way you calculate that is take the log of the hydraulic conductivities and sum them up, and then divide by the number of values that you have, and that equals the log of the geometric mean. So in order to actually calculate what the value is, what k bar is, you determine this value. So take the log, sum them up, divide by the number of values, and that equals p, and then 10 raised to the p, where this is a base 10 log. 10 raised to p is the geometric mean. So for the assignment, you should use the geometric mean to calculate. You'll have at least 6 values of k because you'll do 2 different slug tests. And so take the geometric mean of those 6 values and use that to calculate the flux.